Hello everybody. So today we'll be going over homework 4. Now for part 1 here, we'll be talking about the Broyden-Jacobian update. I've not heard of that before. I have the Wikipedia page pulled up here. And what Broyden's method is it follows the same theory as Newton's method, which is used to find roots of a single-dimensional problem, finding where the x-intercept is, or where the function goes to 0. However, Broyden differs because instead of using a single variable, as so, what it does is it solves a system. So what I mean by system is the function that it solves, f, is actually a column of many functions, f1, f2, however many functions it is. And what Broyden's does is it finds the intercept for each of these. So it'll find the intercept when f1 goes to 0, that intercept when f2 goes to 0. And I'll do it for each one of these. So the way it does that is, if we go down here, is it uses the Jacobian update here, where the updated Jacobian comes from the original Jacobian plus this term here, where up here is this expression here will result in a column vector multiplied by another vector here divided by a scalar down here. And that also has x update that we'll use to actually find the intercept. But what differs from Newton's the most is this Jacobian inverse update. So the Jacobian inverse comes from this Sherman-Morrison formula here, where you have some matrix A plus an update UV transpose, or the outer product of that. The entire inverse of that new matrix, is the original minus this term here. Close that. Let me go back to Broyden's. And so let's go ahead and start writing this out. So f here, f1, f2, yada yada. So, just like if we were going to do Newton's, fk plus 1 equals the original k plus the Jacobian k multiplied by the change in x. Plus 1 minus xk. Now, just like how we would do if we were using Newton's, we are going to pick our x sub k plus 1 such that this goes to 0. So we go down here. This is now 0 equals f sub k plus Jacobian k x. Let me center that a little better. Sub k plus 1 minus x sub k. So now we solve that, we find our x sub k plus 1, but when we go back to plug it in, what we're probably going to find is that this is not actually 0. So we go in here, where this is no longer 0, and what we got to do is we need to update our Jacobian matrix here. f sub k plus Jacobian k plus 1 now, because we've updated it, times the x sub k plus 1 minus x sub k. Now, keep in mind, all of these are matrices. Or, well, f here is a column vector, the f1, f2, and so is xk's here, but the Jacobian is a matrix. The only scalar so far is just this 0. So, now if you look at it, we have a system of equations we can solve. So if you subtract the second equation from the first, we get f sub k plus 1. F sub k is canceled out. And then what we're left with is the Jacobian k plus 1 minus the original Jacobian multiplied by the change in x. Now this is just, don't have to write it out so much. I just change it to delta x, but it's just this term here. So now we got this equation. So you might be asking yourself, well, how do we get the updated Jacobian from this equation? Well, the reason Broyden is so unique is he found a very interesting way to solve this. What he did was he defined a new vector, v, and he defined a v to be perpendicular to x. Now the reason we're saying it's perpendicular here is, say you have a function that works in the x direction. So say your f is like 2x squared plus 7. If you travel along the x, this is going to change. So as you go along the x, it's going to increase. But say you wanted to go along the z-axis instead. Since the z-axis and the x-axis are perpendicular, if you set z equal to 1 here, nothing's going to change. You set z equal to 2, nothing's going to change. So that's why he defined that to be perpendicular. Another reason he did that is when you have two perpendicular vectors, the inner product, it's always going to be 0. And that's going to become very important in just a second. But since our Jacobian only exists along the x-axis right now, where by going perpendicular it won't change it, what we can do is we can say updated Jacobian k plus 1 multiplied by that v vector has to be equal to the original Jacobian multiplied by the v vector. So, get all our terms on one side, we get another equation. J sub k plus 1 plus, or not plus, minus j sub k. Vector v equals 0. So now we have another system of equations. We go ahead and write the other one down here. J sub k plus 1 minus j sub k multiplied by our change in the x equals our updated function value. So now we got this. Now, this is where Broyden really popped off. He saw these, and he first looked at this one, and he said, well, this has to go to 0. This can't be anything other than 0. So, j sub k plus 1 minus j sub k. There has to be a delta x transpose in the numerator. The reason is if we replace this with that delta x, that's going to be 0, no matter what. So we got that solved. No matter what else, what you put into delta x, whatever, once you combine that with that v, it automatically becomes 0. So we got that first equation solved. Now we got to look at the second equation, where this term has to be in here somewhere. So he put it in the numerator. That's f sub k plus 1. And then he saw, well, we got another delta x term here. How do we get rid of it? If you multiply delta x in here, you got a delta x transpose up here. So what he did was he prepared for it by adding the delta x transpose, delta x at the bottom, and the denominator here. So when that got multiplied in, got the same term top bottom, you mark those off. Now, and you're just left with f sub k plus 1. So that's solved. Now if you go back to the first one, you still got that 0, canceling the f, canceling all this, making it still 0. So both of these are solved now. So this is where Broyden's method came from for the Jacobian update. We go down a little bit more, so you can see k plus 1 equals the original Jacobian plus f k plus 1 delta x transpose over delta x transpose delta x. Now, you may be wondering yourself, well, this looks nothing like what's on Wikipedia here. So let's go through and see if the two are actually equal. So we got a delta x transpose here, got the delta x transpose here, so we got that covered. So let's look at the numerator first. Does f sub k plus 1 equal, what was his, delta f minus the original Jacobian delta x. So first let's break this down. Delta f is just f k plus 1 minus fk. Then let's break down our delta x. Or well, let's leave that there, actually. Because all delta x is just xk plus 1 minus xk. So let's combine some terms like so. I got fk plus Jacobian sub k delta x. Now you may see this term here and be like, wait, this looks familiar. That's because if we go back up a little bit, it's this term here. F sub k plus 1 equals f sub k plus Jacobian sub k times the change in x. So, what you can do is we're going to replace that with f sub k plus 1. Or can we? Because remember, we go back up here, we picked our x sub k plus 1 such that this is always 0. So it's not f sub k plus 1, it's actually 0, leaving off just this term, which is what's over here. So that checks out. So numerator is fine, this is fine, now I got to worry about the denominator. Delta x transpose delta x, and now does that equal the norm of the delta x vector squared? Well, let's think about this left side first. So your delta x transpose is going to be a vector that is one row by n elements, multiplied by a column vector that has n rows and one column. And the way that's going to work is we're going to get a scalar value. So x naught times x naught plus x1 x1 all the way up xn squared. So that's the pattern that this is going to follow. So, to write this in summation notation, got from 0 to n of xi squared. So that's what the left side boils down to. Is just take each of the elements n delta x, square them, add them together. Now, if we go over here, the way the norm is calculated is you take the square root of the square of each element. And then if you square that, you get a summation from 0 to n x sub I squared. Notice these two match. So this is good. So we cleared this, we cleared this, we cleared this. So now we know for sure that this Jacobian update is the same as this Jacobian update. So we got that. Now let's sort of look at how he did the inverse of that. So let me open link a new tab. So the Sherwin-Morrison formula, as such, says this. So let me just snip that. Bring that down here. So what it says is that some matrix A plus an update, the inverse of that equals the original inverse minus this term, where U and V are column vectors that can basically allow you to control certain values in it, in a matrix. So, the way this works is we're going to end up replacing A with our Jacobian inverse. Equals Jacobian inverse minus Jacobian inverse here, U V transpose Jacobian inverse once again, and then 1 plus V transpose Jacobian inverse U. Now, all this term on the left side is just an updated Jacobian. So, now we got that. All we gotta do is figure out what our U and V is going to be. So, we go back to Broyden's, and we look at our equations here. So, what we gotta look for is figure out what our U and V vectors are. So, let's go back up here to our Jacobian update. The J sub k plus 1 equals the J sub k, plus yada yada. So, if we go to the actual Broyden's version of it, right here, what we see is we can split this up into two. So the U, in this case, is going to be our numerator here, the delta Fn minus the original Jacobian times a change in x. Go down here, U equals change in F minus K change in x. That's our U. Now our V transpose is going to be our delta X transpose divided by the norm of delta X squared. So, in reality, what we got, if we were to rewrite the Jacobian, we have J, k plus 1, equals J sub k plus U V transposed. Now, the reason we can assign these is U and V are just column vectors. We got a column vector in F here, but Jacobian here is a matrix. So if we were to have 3 F's and 3 X's, it would be a 3 by 3 matrix. But since we're multiplying it by another column vector and a n by 1, what we're going to have a 3 by 1, which is just a column matrix, or column vector again. So that checks out. Delta X transpose is a row. And delta X squared down here is a scalar. So that won't affect the shape at all. So that's why you can assign those values. So, what we can do now is we can start plugging these into this equation here. So, Jacobian inverse k plus 1 equals the original Jacobian inverse, and then that's minus J negative 1 inverse times u delta f minus Jacobian sub k delta x and then v transpose, which is just delta x transpose over the norm squared. And then one more Jacobian inverse. Now all of that divided by 1 plus v transpose x transpose over delta x squared multiplied by the inverse Jacobian and then multiplied by our u vector. Okay. Right. So now we got that. With that, what we can do is we can start noticing some things. First, we got J inverse. We also got J not inversed. If we combine them, we get an identity matrix, where it's just ones and diagonals with the rest being zeros. Dun, 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 dun. And with the identity matrix, it's essentially multiplying something by 1. So we can just get rid of that. So what the numerator is left with now is jk negative 1, change in f minus delta x multiplied by delta x transposed over the norm squared times the original inverse one more time. Alright. So now if you notice this term right here, it looks pretty similar to this term there. All we gotta do is just take negative out, negative j sub k inverse, delta x minus j sub k inverse change in function. Alright, so now we got our numerator there. Now we got to mess with the bottom such that it looks like this. So we can just rewrite the denominator down here. 1 plus our u vector And then we can do the same thing at the bottom here too, did in the numerator. J sub k on change in f minus delta x. So we go back here, we look at it. So we got our delta x transpose, our inverse, and our delta f. But we've got an extra delta x here, and we still got these terms to worry about. So what we can do is multiply it across by the delta x transpose, and we get 1 plus r over delta x squared. Now we got our delta x transpose, our Jacobian, our change in function, or change in function values, minus 1. Because transpose times the original or no. Thinking of the wrong thing there. Minus delta x transpose multiplied by the non-transpose version, and that gets us this term here, the delta x squared. Just like how we did up earlier, right here. So now, if we multiply this across, this cancels out to 1. And then we also got the 1 term there, so those cancel out. And then, so the only thing got left is that scalar here, dividing this. But if we take it up to the numerator, this cancels out. So in reality, this is gone, and this is gone, leaving us just that. And then this is gone. So our denominator is the delta x transpose, the original inverse Jacobian, multiplied by the change in function value. So if we put that all together, we got j sub k plus 1 inverse equals the original Jacobian, add, because remember, we took a negative out here. So in the numerator, we got delta x minus original inverse Jacobian multiplied by change in f. All of that divided by, there it is, our change in x transposed, our inverse Jacobian, and change in f once again. And all that gets multiplied by these two terms here, delta x transpose and original Jacobian inverse. Now, if we go back, look, that's exactly what Broyden has. So, we got our inverse update, and we got our Jacobian update here. Come on, scroll wheel, don't fail me now. right here. So what we can do is head over to Collab. Already got some imports going to help us out a little. What we're going to do is we're going to define a column vector function. And again, buds, you're fine. Sorry, he gets excited for science. But going on with this, what we're going to do is we're going to have f return a JMP array. And then in the first part, we think of what function we could use. Let's do x. So x0 minus, say, 5. Square that. Bam! Move x1, let's say, plus 7. Let's cube that. Make it a little more complicated. Now let's also make another function. X0 minus, let's say, do minus 25 this time. And let's raise that to the fourth. Do x1 plus 2. And let's not even raise that to a power. And then just to make our lives a little easier, let's make this run a little faster. So if you were to time this, array, let's do 1. Runs about 333 microseconds. Alright. So now we got our function we want to solve for. Or find the roots of. So now we gotta define our Broyden. Gotta pass our f. We have to have an initial guess. Just like if we were to do a Newton. It's always got to add max iters. Do 1,000. Tolerance 1e to the negative 10. Broyden. Alright, so now let's go back to Broydens. So what you want to do is we want to use this function here, where we want to update our x values till we get our root. So what we need is we need an initial inverse, we need an initial f, we need an initial x. Now initial x is going to come from x guess. Come back here. Now, for our initial inverse of our Jacobian, what we're going to do is we're just going to have an identity matrix. x1.size. That's just going to make that diagonal ones in the size of x1. So we do that, and then let me see. Got initial, and now I just need initial f. So we do f1 equals f x1. Right. So we have that now. What we want to do is range max iter Okay, that's still going. On range max iter. We're going to run while it's not surpassing the max number of times it wants to run. What we want to do is we want to update our x value. So our x2 equal to our x1 plus our J inverse, or is it plus or minus? It's minus our J inverse multiplied by our f1. So that'll give us our x2. So now we can calculate our f2 using x2. Got that. And then got our updated. Now if our updated value is close enough to 0, we want to break out this loop. So what we want to do is if f2 is less than or equal to our tolerance, we want to return x2. So that'll break out the loop, it'll return that value, it won't run anymore. So we got that. Let's see, is there any? And then if that is not the case, what we want to do is we want to update our J inverse using our formula. Well, actually, so we want that f2 norm. The reason we want to do that is f2 is a vector of values. We want to combine those and get a result that we can check against our tolerance. So from here, next thing we can do is update our J inverse. So update our J inverse by using their equation. So what I'm going to do is dx equals x2 minus x1 dot reshape -1, 1. Well, the reason we have to do the reshape there is we need this in a column vector form. So that'll make it into a however many rows, 1 column. And then also got a df f2 minus f1 reshape -1, 1. Alright, so we got that. And then from there, got everything we need, just need to add the actual equation. So J inverse plus dx minus J inverse multiplied by df. That. Now divide that by the denominator, dx transposed, matrix multiplied by the Jacobian, multiplied by df once again, and then all of that multiplied by dx transposed again, multiplied by J inverse. X2, F1 equals F2, F1 norm equals F2 norm. Alright, so we updated our Jacobian inverse here. Now I just need to update our X and F's. So, and then if this takes too many tries, I want to do, I'm going to raise a value error. Could not converge after iter attempts. Alright. Let's check it out, see if it works. Do Broyden, do RF. Let's do an initial guess of 1, 1. Could not converge. Okay. So, let me look through here. Print. Oh. Why is it giving nans? Is it just a bad guess? Okay. If I change this, say like 5, 6, okay. So yeah, so then it converges. Why would 1 and 1 not want to work? Okay. Well, good news is it works, but it's just that we had a bad guess going on. And then actually, what I'll probably do is jax.config.update units enable X4 processing true. I think I got to disconnect, connect, delete, runtime, run all. Yeah, okay. Yeah, so that is just a bad guess. Yeah, so it just gets too big too quickly. What I can probably do is Let me do dx equals negative inverse at plus dx. For j in range 10. I think what might be happening is I'm just overshooting it. If f2 norm is less than f1 norm, great. If that isn't, half r dx. Okay. So, it ain't giving us nans anymore, but it is just getting too big too quick. So, if I got rid of these powers, right? Yeah, so 25, negative 7, go up here. If our x0 is negative is 25, this goes to 0. If our x1 is negative 7, this goes to 0, 0, 0. Yep. X equals Broyden. F x gives us almost zeros. Alright. Let me just get rid of this part. Alright. So that's been part 1. I'll see you guys in a little bit for part 2.